In this video, we continue our journey of evaluating aldehydes and ketones. Here, we are going to look at reactions that will yield aldehyde and ketone products. The specific reactions that we are going to provide overviews of here are all a review of previous chapters. So the reactions that we will be looking at here are the oxidation of primary and secondary alcohols to ultimately yield aldehyde or ketone products. Ozonolysis, which lysis means to break, ozone is O3, and so ozonolysis reactions will take an alkene starting material, use ozone O3 to cleave the carbon-carbon double bond here, creating in its place aldehyde and ketone products by bringing an oxygen from ozone in there. There is a second step to this reaction as well, where there are a variety of different possible reagents used there, such as DMSO CH32S. Friedelcrafts Isolation, we just learned about in the last chapter, but we will go ahead and include that here on our list, where we are bringing in an acyl group as the electrophile to complete a substitution reaction on an aromatic ring. Alkyne hydration is a throwback reaction to Organic Chemistry 1, where we started with an alkyne using water with sulfuric acid as a catalyst and quite possibly as well mercury 2+ as a catalyst. We were able to create an aldehyde or ketone as the major product there. And as well, with an alkyne starting material, we could do hydroboration oxidation by reacting with borane, BH3, followed by H2O2 and sodium hydroxide to give ultimately an aldehyde or ketone product. So these reactions are going to give us several possible routes to ultimately yield aldehyde or ketones as the product of our reaction. So if we're doing a synthesis where the targeted product of that synthesis is an aldehyde or a ketone, these are good resources to look back at and think about what is the particular scenario you're working with and how could you get to that aldehyde or ketone destination that you are aiming for. So let's take a closer look at each of these 5 reactions in a slight bit of more detail. I'm not going to go through any mechanisms in this video. Instead, what I'm going to do is remind you of key features that you need to be aware of when using these reactions to predict products. We are not doing mechanisms because we did the mechanisms for most of these reactions back in previous chapters. So let's go ahead and take a closer look at alcohol oxidation and the nuts and bolts of that to enable you to predict the products of those reactions. As we consider alcohol oxidation, let's break it down based on the type of alcohol that we are dealing with. We're going to start with secondary alcohols, whereas secondary alcohol is referring to an alcohol where the carbon that is directly bonded to the hydroxy group has 2 other carbons directly bonded to it. And so it has to fit the general template that we have here where our carbon that has the hydroxy group has 2 other carbons bonded to it. In cases such as that, what is going to happen is if we treat that with an oxidizing agent, common oxidizing agents here will be chromium-6 reagents. I'm going to abbreviate that as CRVI, such as a common example of a chromium-6 reagent being chromic acid, which is H2CrO4. So I'm just going to put that in as one possible example here, but there are a variety of different chromium-based oxidizing agents. So this is far from the only one. And so you'll want to take a look at what's available in your reaction mixture if you're trying to decide whether an oxidation is going on or not. And if there's chromium-6, oxidation is a good bet because that is a strong oxidizing agent. An alternative to that is literally bleach. The reason why bleach is effective as a disinfectant is because it is a very strong oxidizing agent. And by strongly oxidizing cellular components, particularly of microorganisms, it will essentially destroy the viability of that microorganism. And so that's why bleach is very effective as a general agent for sterilizing materials. So looking at a secondary alcohol, treating it with an oxidizing agent, what is going to happen when treating with an oxidizing agent is that the hydroxy group is going to be converted into a carbonyl group by removing the hydrogen that is directly bonded to the carbon here. So the hydrogen-carbon bond is going to be removed, and a pi bond is going to go here to make a carbonyl group. So the way that we can go ahead and write out this product is that we're converting that alcohol group into a carbonyl group is the bottom line here. So the bottom line scenario, when you're thinking about using and applying this reaction is that secondary alcohols are going to be converted into ketones by oxidation. So this product here will always be a ketone if you start with a secondary alcohol, because you're converting this hydroxy group into a carbonyl group. That carbonyl carbon is flanked by two other carbons, meaning this is ultimately a ketone functional group if you start with a secondary alcohol here. So what if instead we started with a primary alcohol? So if we start with a primary alcohol here, and we begin our oxidation pipeline, we are starting with a primary alcohol. That means it has only one carbon bonded directly to it. So therefore, the carbon that we're working with here, the one that I'm putting the hydrogens on explicitly, has two hydrogens directly bonded and the hydroxy group. What's going to happen in an oxidation reaction there with those typical oxidizing agents we list above, where I'll just plug in O here as our generic oxidizing agent. So oxidizing agent up top here, just labeling as O in brackets. If we oxidize the primary alcohol one time through one reaction of oxidation, what's going to happen is that one of the carbon-hydrogen bonds is going to be replaced with a carbon-oxygen double bond, like so, so that you would create, out of this first oxidation here, an aldehyde group, because you have a carbonyl directly bonded to a hydrogen atom, giving us, therefore, an aldehyde. Here's the deal, though. Aldehydes are generally more susceptible to oxidation than primary alcohols. And so this aldehyde group, once it forms, immediately reacts with additional oxidizing agent to be transformed into the further oxidized molecule, which is the carboxylic acid. And in making that carboxylic acid, what we're doing is replacing this last remaining carbon-hydrogen bond here that I'm highlighting from the aldehyde with a carbon-oxygen double bond through that additional oxidation. And so looking at this, with the reaction being generally very hard to stop or practically impossible to stop at the aldehyde step with standard oxidizing agents, such as the ones we list above, being the typical chromium-6 reagents, or bleach, we need some alternative method if our goal is to take a primary alcohol and end with an aldehyde rather than the aldehyde getting oxidized all the way to a carboxylic acid. And so how do we go about doing that? Well, there are specialized oxidizing agents that will enable the reaction to be poisoned at this step, at the step of converting the aldehyde into the carboxylic acid, so that the reaction will hence cease at the aldehyde product rather than continuing onward to the carboxylic acid. And the two main reagents that we recognize and can apply toward the selective oxidation of an alcohol to an aldehyde product rather than continuing the reaction on is that we can stop the oxidation at the aldehyde by using PCC or PDC as our oxidizing agent. So stop the oxidation at aldehyde by using PCC, which stands for pyridinium chlorochromate, or as an alternative to that, PDC, which stands for pyridinium dichlorochromate. So if you are looking at or designing a reaction and you wish to take a primary alcohol and convert it into an aldehyde product, you definitely want to use one of these specialized oxidizing agents, PCC or PDC, which will enable the reaction to stop here at the aldehyde stage rather than continuing onward to a carboxylic acid. So don't envision that you can just dump bleach into the reaction mixture of the primary alcohol and get an aldehyde out. Instead, reacting with bleach would carry on the oxidation all the way to the undesired carboxylic acid product. So we've done primary alcohols, we've done secondary alcohols. What about tertiary alcohols? Just to fill in the lineup here, what happens if we try to oxidize those? So if we take a tertiary alcohol and we attempt to react that, tertiary alcohol by definition is going to have 3 bonds to other carbon atoms, so 3 bonds to other carbons, and our hydroxy group here. When we treat a tertiary alcohol with these typical oxidizing agents, meaning any of the ones listed above here, there will ultimately be no reaction. And the reason why there's no reaction here is that there are no remaining carbon-hydrogen bonds to break at this reactive carbon center here, the carbon that's directly bonded to the alcohol group. So here we just have carbon-carbon bonds. Those generally are quite stable and resistant to breakage. And so as a result, there's no good bond to break here to carry out an oxidation at this carbon, and hence there is no reaction. So it has to be primary carbons or secondary carbons, where in both of those cases, we're replacing a carbon-hydrogen bond with the carbonyl pi bond. So that is our alcohol oxidation. It's one of our ways of creating aldehyde and ketone products in this overview of reactions that we've looked at before. Let's move on to the next reaction type, which is ozonolysis. In ozonolysis, what we need to be aware of in general is that this reaction is going to allow us to convert an alkene into two aldehyde or ketone products. So what is the general layout of this reaction? Well, the generic layout is that we start with our alkene. I'm going to plug on the R groups here, which I will just refer to as R, R prime, R triple prime, etc. And the reagents that we will use for that, first and foremost, and the way you'll recognize a reaction is ozonolysis for sure, is that the first step will involve treatment of the alkene with ozone. And then the second step, there's some variability here in terms of exactly what is used. Common is dimethyl sulfoxide, DMSO, which is CH32S. And the outcome of this reaction is that the carbon-carbon double bond right here will be broken, and that carbon-carbon bond on both sides will be replaced with a carbonyl group, with the oxygen being donated from the ozone. And so as a result of this reaction, what we will get is our R groups there are still all in place as they were. So I'm just going to plug those all in. Our carbon, that is the carbon that was on the left, which I'm highlighting in yellow, will become a carbonyl group in place of where the carbon-carbon double bond was. And then similarly, the carbon that was on the right side of our alkene group, plug that in green, plug that carbon in green, is going to be a carbonyl group as well, with the R groups attached to it here. So going on and plugging in my R groups, R and R prime. So this is going to, as a result of our ozonolysis reaction, create two aldehyde or ketone products. And whether we create an aldehyde or ketone is dependent upon what the structures of these R groups here, because the R's at the beginning of the reaction can be either hydrogens or alkyl groups. And if you end up in a situation where both of these are, one of these R's or both of them is a hydrogen, then it will be an aldehyde. If both of these R groups are alkyl groups, then it will be a ketone product. And so this is a convenient way to go about taking alkene starting material and converting it into aldehyde or ketone product. So we'll do a specific example here before we move on to the next situation to illustrate what we can do with this. So we're doing ozonolysis. We recognize those ozonolysis because O3 there. Just plug in my reagents. So the way that we can envision this happening, I'm going to draw a squiggly line through this to remind myself that I want to put a carbonyl group in place of that alkene group on both of those two carbons that were part of the original alkene group. So I'm drawing in carbonyl group in place of the alkene for the carbon that was on the left right here. Do the same thing for the carbon in blue that was on the right, and I'll go ahead and draw out the product for that side. Drawing in my carbonyl group, drawing my two carbon chain, and then if I want to, you don't have to, but you can draw in the hydrogen there explicitly just as a reminder that it is there and it is an aldehyde group here in this second product. So this is an illustration of how you could design a reaction so that it has both an ketone and an aldehyde as the product of this ozonolysis. And if you make The R group's symmetrical on both sides, like R triple prime is the same as R prime, and then R up here is the same as R quadruple prime, then you would create two identical aldehyde or ketone products as a result of that reaction. So let's go onward to our next type of method for creating aldehyde or ketone products in this review, and that is Friedelcrafts Isolation, which I will touch on just briefly so that we have a comprehensive list here of ways to go about creating aldehyde or ketone products. But we're not going to get into much depth on this one at all because we just covered this in the last chapter. So in Friedelcrafts Isolation, what we're going to do is react with an acyl halide. So acyl chloride there, aluminum chloride catalyst. And the outcome of this reaction is that this is a typical electrophilic aromatic substitution reaction. And so one of the hydrogen atoms from our aromatic ring is going to be replaced with the acyl group. If we were starting with something other than benzene here, we would need to be aware of the role of directing groups, that is whatever's already attached to the ring, acting as an ortho-para-director or a meta-director to determine where exactly to place that carbonyl group and the associated R group, the alkyl group, or whatever else is directly bonded over here. So this is a commonly used way to create a ketone functional group onto an aromatic ring. This Friedelcrafts isolation is not a useful method for creating aldehyde or ketone groups in other contexts where there are no aromatic rings, but it's a great way to attach an aromatic ring with a aldehyde or ketone group here by using a so-called acyl halide. Let's go on now to our next strategy for creating aldehydes or ketones, and in this particular strategy we're going to start from alkyne starting materials to continue our tour really of different starting materials we can use to create aldehyde or ketone products. So in this we're going to call this hydration because we're going to be adding water, H2O, across a carbon-carbon triple bond. So we'll call this hydration of alkynes. And we will go ahead here, and in the hydration of alkynes, the general reaction is going to be that we start with our alkyne, like so, and we react it with absolutely water in order to carry out a hydration. And then the reaction is catalyzed by sulfuric acid and commonly as well mercury 2+. So those are our catalysts for the reaction. And what's going to happen in this reaction is that the water will add across the carbon-carbon triple bond to give an enol intermediate. So the water comes in and the pi bond comes over. It's going to form a covalent bond via one of the two carbons to a hydrogen, the other one to the hydroxy group following Markovnikov's rule. Markovnikov's rule saying that the hydrogen that adds is going to go to the carbon that has more hydrogens to start with. The hydroxy group goes to the less hydrogen substituted carbon, or the more alkyl substituted carbon, in other words, is the one that picks up the hydroxy group. And that reaction, as a consequence, is going to result in one of these two carbons picking up a hydroxy group, the other one picking up a hydrogen, and one of these three pi bonds going away to give us what we refer to as an enol. So the enol is going to have a double bond in place of where the triple bond was, plugging in my carbons as they were, my R and R prime as they were, and then we are going to go ahead and put in a hydrogen on one of those two carbons, hydroxy group on the other. So we have effectively added water H2O across the carbon-carbon triple bond, resulting in this enol. Here's the thing though, the enol group is notoriously unstable, and in the vast majority of situations, the enol is going to rapidly undergo a process that we refer to as tautomerization to be converted into an aldehyde or ketone product. So we call that keto-enol tautomerization. And the keto form here, keep in mind, doesn't mean it has to be a ketone. The keto form is just our generic way of saying that this is an aldehyde or a ketone product that will result from this. It's going to be a carbonyl containing compound that is an aldehyde or ketone. And the way that you can recognize what aldehyde or ketone exactly is going to result from this tautomerization process is that the carbonyl group will go wherever the hydroxy group is. So the carbonyl group in this case would go right here where I'm highlighting, and the double bond will no longer be present. It will just be a carbon-carbon single bond there to avoid going over the octet rule. And so I'm going to go ahead and fill that in predicting the product of this reaction, that the hydroxy group ultimately is a carbonyl group. R prime goes over here. Single bond will connect the two carbon atoms. And then we will have over here on the other carbon to fill its complete octet. I'm just going to make my arrow a little bit shorter there so that I have room to fill this in without totally squeezing. We will fill in an extra hydrogen here to fill the complete octet on this carbon. So rather than having one hydrogen over here, now we'll have two. And we'll go ahead and fill in our R group there as well. So let's do an example of this where we can actually dig in and apply Markovnikov's rule to make sure that we have a good recollection of what we're doing with this. So I'm going to create a asymmetrically substituted alkyne. That is an alkyne that has a hydrogen on one side and one or more carbon atoms on the other, so that there is some regioselectivity via Markovnikov's rule to this reaction. I'm going to say we're treating with water, sulfuric acid, which I'm just going to abbreviate as H+, because we just need a proton donor in there, and then our mercury 2+. And what's going to happen here, if we were asked to provide the enol, which I will just sketch out en route to what we would actually observe as our final product, which would be the keto product. In our enol product, or intermediate, I should say, to be more accurate, we will decide which of the two carbons of the alkyne are going to pick up the H and which is going to pick up the OH. So the one on the right is the more alkyl substituted. And so that is going to be where the OH goes. On the other hand, the carbon that has more hydrogens to start with is going to be the one that picks up the proton. It is the less alkyl substituted, in other words. And it is going to pick up the hydrogen atom. That is a description of Mark's rule. So, in drawing out our enol, draw out my carbon-carbon double bond here. And I'm going to plug in the CH2, CH3 group, the R group that was over here, I'm just carrying over. And then our OH group that has come in, I'm going to put in red for emphasis, so I plug that in. The hydrogen that has come in, I'm going to put in red for emphasis. And we already had one hydrogen over here, which I'm just going to sketch in black. So this is our enol. And then via that keto-enol tautomerization, there's going to be an equilibrium that very strongly generally favors the so-called keto form, where the keto form, I remind you, can be either an aldehyde or a ketone, depending upon what the structure of the enol is. And so what we are going to do to make the keto form is replace the single bond to the hydroxy group with the carbonyl group, convert this into a single bond rather than a double bond, and plug in a hydrogen as necessary to be at the octet rule for this. So drawing in my carbonyl group, carbon, CH2, CH3, carbon-carbon single bond coming across through here. So I'm drawing my single bond down here that matches where we had the double bond up there in our enol form. We come over to here. This is our carbon that is on the left right here is the one I drew down here. It had two hydrogens. It's going to have a third one, so I'll go ahead and put that in as CH3 in this keto-enol tautomerization process. So our final product of this reaction that we would actually observe in our reaction flask as the main product is going to be this keto form. And now finally, we will go ahead to our last reminder or review reaction type that will yield an aldehyde or ketone product, and that is going to be the hydroboration oxidation of alkynes. This reaction is analogous to the hydration in that it's going to give the addition of H and OH across the carbon-carbon triple bond to give an enol intermediate that is then rapidly transformed into primarily the keto form at equilibrium. The difference between hydroboration oxidation and the hydration reaction we just looked at is that the regioselectivity is opposite. So in hydroboration oxidation of alkynes, what's going to happen is that we are going to go opposite Markovnikov's rule. So we still will take our starting alkyne. This time we'll react it with borane, BH3, or alternatively B2H6, you may see it as, followed by peroxide H2O2 and base. And the outcome of that reaction is initially that we create the enol. So this is our enol intermediate that then, much like the hydration reaction, is going to undergo tautomerization, where the equilibrium is going to strongly favor having a carbonyl group in place of where the hydroxy group was. Fill in your R groups and fill in the hydrogens here to have a complete octet so that we end up with this so-called keto form, where the keto again can be an aldehyde or a ketone. Don't let the term keto make you think that it has to be a ketone. So in this reaction, what you need to be aware of that's going to distinguish this in terms of the product that you will predict relative to hydration is that it is going to go opposite Mark's rule. And so let's do an example of how we can illustrate this going opposite Mark's rule with an actual reactant. So I'm going to start with the same reactant that we did last time, like so, to illustrate how the regioselectivity of this reaction with hydroboration oxidation is opposite the regioselectivity of the hydration reaction that we did a couple of minutes ago. So bringing in my hydroboration oxidation mixture, what's going to happen here is that following this premise that we're going opposite what Mark's rule would predict, what we do is that we look over here, and this is our more alkyl substituted carbon. That is what is going to pick up the H. That is the opposite of what was happening in the hydration reaction where we were following Mark's rule. Likewise, our less alkyl substituted carbon, that is the carbon that has more hydrogens directly bonded to it, is where the OH is going to land in this reaction. And so as a result, when we go out to draw our enol intermediate, can go ahead and draw that out here. We're going to plug our new hydrogen in over here on the more alkyl substituted carbon. And then on the other side, we are going to have the hydrogen that's there to start with, as well as our hydroxy group is going to go on that less alkyl substituted carbon. So this giving the opposite regioselectivity of the hydration reaction is really useful because it will allow us to control where the hydroxy group goes within the molecule to create the correct constitutional isomer. The enol intermediate rapidly tautomerizes to the keto form, and so we can go ahead and show that product as well. This is going to be your major organic product, is this final product that we create here. The enol is just an intermediate because in the majority of cases, the tautomerization favors the so-called keto form. So we've made our keto form here by taking the hydroxy group from the enol, converted into a carbonyl, and the double bond that we started off with has become a single bond, and importantly, we have plugged hydrogen in there where I just listed here so that we have a complete octet there in our so-called keto form, which in the case of this keto form, notice there's actually an aldehyde functional group here. We still call it that keto form. So don't let it confuse you in these reactions. We, as I mentioned at the beginning of the video, did not do any of the mechanisms for these reactions. If you are interested in the mechanisms, those are covered in earlier chapters for these particular reactions. But for purposes of what we are doing now here at our later stages of organic chemistry 2, we're interested primarily in applying these methods toward the synthesis of organic molecules. And in the interest of that focus here and the fact that we've done the mechanisms before, I did not go through any mechanisms in this video.